If you find these videos helpful, please consider supporting AddOhms and the Bald Engineer on Patreon. Hello, my name is James, and welcome to an AddOhms Bald Engineer live stream. So the last couple of streams we've been talking about MOSFETs and a MOSFET test board that I designed. On Sunday, we encountered some measurements I did not expect. So in this stream, I'm going to explain what I found, at least as much as I understand up to this point. And I'm actually preparing this for a video. So let me say hello to everybody in chat. Thanks for playing the trivia. If you can hear me okay, please say hello and your favorite component, which I've decided from now on is going to always be my thing, is asking what your favorite component is. So let's do that and see how things are going. I'm going to drink some tea while I check the audio. All right, and the first response I see is from Dexter. Looks like audio is doing pretty good. Awesome. Had a little bit of a snafu right before I started. Realized the batteries in my microphone were dead. So a 222 transistor, a 65 B816. Is that the processor that's in the Apple II GS? That number looks really familiar to me, but I don't fully recognize it. And I've missed that one before. Oops. Okay, so just as a quick reminder, I do stream to multiple platforms. So on YouTube, it's AddOhms. On Twitch, Bald Engineer, and I'm also streaming to Facebook. But all three of those places, the chat comes to one. So I will see your messages on all of them, and hopefully they'll show up on the screen somewhere. Oh, I almost got it, like right here. So that's going to move around in just a second. Okay, so what are we going to talk about? Well, let's go take a look at my laptop. And what I'm targeting is, this is the circuit board, or the circuit that we designed. And we designed this a couple weeks ago, then had a PCB made. PCB came in, and on Sunday, I think it was Sunday, we made some measurements, and I was like, I got some measurements I didn't expect. But before we get to those, so we've got a MOSFET, and then the whole point of this board was I wanted a shunt resistor so that I could measure the current going into the gate. Huge misconception about MOSFETs is that current on the gate doesn't matter. Now, it doesn't matter like it does for a BJT, but even though they are voltage controlled, the current going into a gate is not zero, and that's what we're going to talk about tonight. Now, it turns out that we haven't actually made this measurement, the whole point of the board. We haven't made that one yet because I don't have the right value for shunt resistance, and so we can't really do that. But we can measure some cool stuff nonetheless, and we're going to. And then we want to look at, okay, and so what we're looking at then is what happens if you do have a current limiting resistor on the gate versus if you do not. When I did the MOSFET video for AddOhms, a ton of people have asked me about the gate resistor that I showed and then didn't really explain. I've also had a lot of people try to tell me that I'm wrong and you don't need a gate resistor. False. Sometimes. This board also has pads for pull-up and pull-down resistors as well as a capacitor so that we can slow down the edge of the gate. However, we are not doing anything with those three. So for all the measurements we talk about today, these three components are not populated. You can ignore the shunt resistor, just consider this a short, but I have two versions of the board that looks like this one. So I've got this board, I've already got one hooked up, and like I said, I've got two, and on one of the boards, I have a 3K resistor, and on this board I have a 0 ohm resistor. And so that means that we can see what would happen if you did not have a gate resistor at all. Okay, that's not the one I wanted. All right, so now where were we the last time? And then I'm also going to show you what we're going to see, and then I'm going to show it to you live on the scope. So last time we hooked up, this is not it. Why did I load the wrong screenshot? Okay, no problem. I will make this work. Oh, I know what's going on. I didn't load. Oh, silly, silly, silly. I know why, because the screenshots I want it. We'll just find it real quick. Here we go. So here's the first thing we saw on our oscilloscope with a 0 ohm resistor. So let me explain everything that's going on. The orange trace is channel 3. This is the gate. The yellow trace is the voltage of the drain. And then the green trace is the current through the drain. And so one thing we didn't do on Sunday is we didn't measure any of the current through the drain. Well, I'm using my current probe so that we can see that. So this is the voltage across the MOSFET, and this is the current through the MOSFET. And then this blue line is a math function, which we're not going to worry about for the moment. So here's the thing. We're driving this with an Arduino, which just reminded me we have to reprogram the Arduino before we move on. But we'll do that in just a second. So here's the gate, and we're driving this with an Arduino, and on the Arduino, all we're doing is digital write high. So this is actually going from 0 to 5 volts. But look what's actually happening on the gate. It goes up to a few volts. I think this is right about 2.5 volts or so. It rings, and then it plateaus, And then we see this behavior. Believe it or not, this is actually typical of a MOSFET turn on. And this actually illustrates why MOSFETs are not just as simple as you look at the voltage, the threshold voltage, and that's how you turn it on. One of the things we want to control is how fast does it turn on, and we do that by controlling how much current goes into it, because this is showing us a capacitor charging up and then another capacitor charging up. Okay, anyway, I'm getting ahead of myself. So gate turns on, and then here we see the voltage of the drain. So right now it's open, and then it suddenly starts to close, and so that's why we see the voltage drop. And this rate of drop is the output capacitance of the MOSFET. And as the voltage drops, current goes up. And so Ohm's law says that, you know, as current starts to flow, the voltage through the device. What am I trying to say? Ohm's law tells us how much power the transistor is dissipating. That's what I was trying to get to. So what's important with okay, so that's what we saw. What I didn't understand was why did we see this Miller effect? This is called a Miller Plateau. Why did we see that? And what I didn't realize is this is actually when the MOSFET starts to turn on. For some reason, I thought the turn on happened after the plateau, but I was wrong. Went back, reread my books, and realized what's going on. Now, here is the subtle problem, and we're going to see why this is a problem when I get to the scope. See how this is the drain voltage. So this is the voltage across our device. Notice how this is at 12 volts, and then it spikes up to almost 14 volts, and then it comes back down as it turns on. This inductive spike, it can actually be a very bad thing. And it's bad for two reasons. One is because it means our voltage is going above whatever the load voltage was. And two is this is a source of EMI. And so while we do want the transistor usually to turn on as fast as possible, there is a negative consequence to having it turn on too quickly. So that was with our 0 ohm board. And then here's what the waveforms look like with our 3K board. So just like before, the orange trace is the gate, the yellow trace is the voltage of the drain, the current is the green trace, and then the purple trace you can ignore for now. We're going to get back to that. The three that are really important are the orange, yellow, and green. So notice how with the 3K resistor, there's two things that really are interesting. Number one is the gate does a really nice change from 0 to 5 volts. Now this is actually relatively slow. It's much slower than what the previous shot showed, but there isn't that whole ripple or plateau effect that we saw. Which also means when we look at the output of the MOSFET or the drain, notice how it's basically 12 volts and then it falls down. And so we don't get that inductive spike, and then what that also means, we don't create a bunch of EMI. Here's the bad part, and I'll explain this again when we get to the scope, is this amount of time is like, I want to say this was on the order of 70 or 80 microseconds. What are we at? 4 microseconds per division. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, 40 microseconds or so. And the previous screenshot, it was 100. It was 1 microsecond. It was like 900 nanoseconds. So this means with the 3K resistor, we don't get a ring, but look how slowly our MOSFET turns on. That's really important because if we look at the volt or the power dissipated during this time, there's heat being generated that is basically loss. And so the way we pick the gate resistor on the MOSFET is a difference between how quickly we want it to turn on versus how much power are we willing to let it dissipate or lose during turn on. And I'll show you why we don't want to just slam it on without a gate resistor. Okay? Everybody up to speed with what's going on? I know that's a lot, but we're going to get to lots of really cool stuff. Originally what I was going to show you was, I was just going to say, if we look at this screen, if we look at these screenshots, by the end of this stream, I will have explained everything we're looking at one step at a time. And that is what we're going to do. Hey, Scope Wizard, how you doing, man? Now I'm a little bit nervous because this is a very scope heavy stream today. And I'm afraid he's going to catch me on the things I don't know how to do. So let's move over to the scope and I've got that fired up. Let me pull up, I think it was in Firefox. Uh-oh, connection lost. That's not good. Okay, we're back. All right. DefPalm, the spike on the Arduino output was interesting too, as though the MOSFET was leaking to the gate and pulling it up. Oh, I totally forgot. I needed to explain something. Okay. If you look, and actually, since this was brought up in the chat, we need to talk about this. This is going to be a really critical, important thing. And by the way, if you don't catch or understand everything we're talking about in the stream, don't worry. Number one, if you go to Twitch, you'll be able to watch it over. But I am working on a concise, edited video that explains everything I'm talking about. So part of this stream is me kind of walking through these explanations so that I can write a video. So I do plan to do a full video on this, and that will likely show up on Element 14 Presents. Right now, I'm thinking it's just going to be called MOSFET measurements. But as was it DefPalm? So if you notice, let's see where. Oh, it was on. It was over here. So one thing to notice. So this is a really critical thing. Is why does so this is with 0 ohms. It's the first thing we're going to look at on the scope, and I want to explain this now, and then I'll explain it again after we see it on the scope. So the gate comes up, it has this ringing, and then it plateaus, and then it charges up. There are actually 2 capacitors in a MOSFET. Okay, there is a capacitor between the gate and source, and if you really think about the way that the symbol for MOSFET's drawn, this is actually sort of indicating that there is a gate capacitance. And so this is probably the most well-known capacitor in a MOSFET, and this can be on the order of 300. So on the FQP 30N06L, the one that we're using in our measurements, this is on the order of about 300 picofarads. There's also a capacitor between the gate and drain. And so when we look at, and let's see if I can get these both on the screen at the same time. And so when we look at, let's do this, and then I'll put this one right here. So when we look at this turn on, so this is the gate, this is the signal from the Arduino. This initial rise and ringing is from the gate capacitance. And so from gate to source, this is caused by that capacitance. And so what happens is this capacitor has to get charged up before the MOSFET can turn on, which is why this gets to about 2.5 volts, which is the threshold voltage for this particular MOSFET, and then it starts turning on. And so this plateau period, which is when the drain starts to open up or become conductive, this period from about here to here is where the capacitor between the gate and the drain starts to charge up. And so there's 2 capacitances that charge up, and that's what we see in this waveform is here's the gate capacitor charging, and then we plateau for a little bit, and that's while the voltage on the drain is dropping. And because it's dropping, it's having a field effect between the gate and drain. And then once the drain drops, then we see the gate voltage rise all the way back up. So now the capacitors are able to finish charging. So when you look in the data sheet, and we could go look at it, but the only thing I want to say is there are values for these 2 capacitances. However, don't misunderstand, they are not static values. These capacitors are dynamic and they change during turn on, which is one of the reasons, I think I just launched VMware, yep, which is one of the reasons we get this ringing. Partially because there's some inductive effects on the MOSFET, but also because the capacitances of the MOSFET are changing. Okay. Here's some tips when you design a board. Make sure you put checkpoints. Yeah, actually, in fact, when we designed this board has tons of test points, and I have some cool like surface mount things I'm getting that Peter from 1 Bit Squared recommended. But it is actually recommended when you do a MOSFET design, you should include test points for the gate and drain so that you can actually measure these effects to see what's happening. So MOSFET measurements. You won't believe what happens to your device when you don't use a resistor on the gate. Okay, that's going to be a better title. Okay. Cool. Let's get over to the scope because I want to show these measurements live because I think it's going to be pretty cool. And I'm recording it so that I can reuse this later. So let's go to, let me show you real quick, explain real quick what I've got going on with the test boards. Zoom out a little bit. My desk is an absolute mess at the moment. It's unbelievable. Oh shoot, I forgot. There's one more thing I want to explain, but I'm not going to. A big difference from the measurements we made on Sunday's stream is I am now using a 100 ohm resistor. The reason I'm using this resistor is I found out that my electronic load, when the transistors were turning on, it took it 250 milliseconds. So I'm sorry, here's the transistor. Or here's the resistor that we're using. I switched to a real resistor because I have an electronic load, and that electronic load was taking 250 milliseconds to turn on, and it was completely screwing up my measurements. And so I took the load out of the picture. We have a static load. It's a 100 ohm resistor, and I have it hooked up off screen to a 12 volt power supply. The test fixture we have, the gate is connected to an Arduino Uno, which we're going to reprogram real quick. I just remembered we have to do that. And then I have a scope probe on the gate, a scope probe on the drain and source of the MOSFET. And then we also have a current probe clamped around the wire that's providing current into the drain. So that way we can see the gate, the drain, the voltage of the gate, the voltage of the drain, and the voltage, and the current of the MOSFET. I also have a secret probe hooked up to a fourth channel, and I'll get to that. So you'll have to stick around to see what's going on there. Okay, first thing I want to do is I've got to get, because I was playing around with this last night, and I ended up changing my Arduino code, and we need to change it back. Otherwise we won't be able to make the measurements we need to make. Okay, so let me just make sure this is out of the way. I can plug this in, and then we'll launch Arduino. All right. Is it an alien probe? No, it is not. Although, I mean, it kinda has a alien look to it. Okay. So let's see, did it load the last thing we had? Nope, of course not. What was yes? So I think this is going to be fine. Yeah, I think this is what we had going the other day. Basically, it's just turning the pin on every... oh, you can't see that. I need to switch over to this screen anyway. So let's do that. So all this code does is set up an output pin, and then we're using millis every second to swap the state, and then we output the state of the pin. So yeah, this is what we want. Make sure this is connected to the correct board. What is COM10? I don't have that many things. Okay, let's upload that. Make sure that's happy, and then I can plug the thing back in and turn the power supply on. I'm gonna get some music going. That way I don't feel the need to sing, because you guys would not appreciate that. All right, so that's uploaded, so I should be able to plug in pin 3 now. And I see a little bit of action on the scope. Turn on my power supply, and I see my supply turning on and off, so we're in good shape. So now let's go over to our scope. RJ says this is not a asks, is this not a karaoke stream? Unfortunately not. You know, I'd like to think I have some unique talents in this world, and I promise you, singing is not one of them. Not even a little bit. Okay, so we can see there's some stuff going on the scope right now. The way I've got this set up is channel 3 is connected to the gate. I'm going to turn off channel 1 for the moment because I want to do this in order so we all know what's going on. And then I want to be able to trigger on the gate signal, so we're going to switch to channel 3. And then I'm going to move the trigger signal up a little bit and put the scope into normal trigger mode. And that means it will only update the screen when it gets a valid trigger, because right now our signal is only updating once per second. And I'm just turning the knob because it's a little bit easier for me. Let's move this down. I'm going to make the gate signal nice and big, and then I'm going to expand the scale out. And so here we can see that effect we were talking about. So I'm definitely looking at the gate. So the signal turns on, we get our ring, Miller Plateau, and then it charges up. Now I'm going to turn on channel 1, which is the voltage of the drain. And I need to turn that as high as the scope will let me put it, because I'm right on the edge of what this probe can do. I'm just going to drag this down. And by the way, I mean, you can do all this on the front panel of the scope, but I'm trying to use the mouse just so you guys can see what I'm actually changing. But I'm still going to use the mouse or use the front panel every once in a while just because habit. I need to turn this off. Okay, so now we're looking at the voltage of the drain. And in fact, let's go ahead and add a label. And the label is, did I already type in drain? I can never remember. I thought it was already in here. Guess not. All right, so we'll just do DRAIN. And on channel 3, we'll edit that label, and this will be gate. And then you can see them because they show up really super big down here. Down here somewhere it says gate and drain. So if somebody asks, please, if somebody asks in the chat what we're looking at, hopefully somebody else can try to help and say, orange is the gate, yellow is the voltage of the drain. Now, let's see the current of the drain. So I'm going to turn on channel 2, and the scope knows that it is a current probe. What are you doing? All right, and now that is not what I expected. Uh-oh. Uh-oh. What am I? Oh, because we're not anywhere near. There we go. Okay, so we'll bring this down to here. Now, one thing we'll have to keep an eye on is when you use a current probe like this one, these Hall effect sensors actually get magnetized over time, and so we'll have to demagnetize it in probably about 10 or 15 minutes. So we'll have to keep an eye that if we see that the probe starts to drift up, then it's time to demagnetize. I meant one of these probes. Let me catch up with chat real quick. Is Arduino really important for communications engineering student? I mean, I think Arduino is important if you're doing anything with electronics, just because it enables lots of things. In my last company, I worked for a capacitor company. The electrical engineering team that built the machines that manufacture capacitors, they actually prototyped a lot of stuff with Arduinos and then moved over to PLC and control systems later on. So I think it's important. In the middle of designing inductive heating for hard to remove fasteners but need high switching current MOSFETs. Okay. Oh, Captain Solo, hey, good to see you. How much time is tolerable for Raspberry Pi 3 to turn on without problems? Can somebody else in the chat answer that one? And then Oscope Wizard brings up, I hope you deskewed the probe. Actually, actually, I did. I tested, I came up with a test procedure to verify that it's close enough. There is a skew in terms of time between the voltage and the current measurement, just because of the way that the probes work. But two things, we're pretty close. We're pretty close with the measurement. It's not perfect because I don't have a D-skew fixture, but nice try. You didn't get me on that one. Okay, so that's what we're looking at now. Is I've got my gate turns on, it plateaus, the voltage of the drain starts to drop. At the same time it starts to drop, the current starts to go up, and then eventually the MOSFET gets fully turned on, so it's dropping practically 0 volts because it's fully on, the channel's wide open, which allows our full current to flow through it. Make sense? All right, so I'm going to use this. I'm turning this position knob. I just want to, this way we can kind of see the cool stuff that's going on. Let the scope update. So, by the way, because I'm a total nerd, I just want to say when I got this to show up, oh, it's over here. When I got this to show up on my scope, I was super excited because this is something I had wanted to measure for a very long time, and I was finally able to. Now, you might be saying, but James, this is, there's no current limiting resistor, it's fine. The MOSFET turns on. If you've ever read anything about MOSFETs, you might have read about the Miller Plateau. We see it, it's supposed to be doing that. Why is there anything wrong with this circuit? So, that's a valid point. The first thing I want to point out is how long does this turn on take? So let's measure that and remember it because we're going to compare it to the other circuit. And then I'm going to show you my magic probe that explains where one of the major problems is. So I'm actually going to use the knob on this because the mouse gets kind of funny for me. So what I want to point to is this is when I'm going to say that the MOSFET is starting to turn on. And then I'm going to move this cursor over here. And this is, to me, is when it's finally turned off, roughly in this period. So I have a cursor from here to here, and that time is 100 nanoseconds. So I said that wrong earlier. I thought it was 1 nanosecond, but this was 100 nanoseconds. So that's pretty fast. I mean, that's not taking very much time at all. So that's cool. But, two things. Or one thing I want to point out, this inductive spike is relative to how much current is going to eventually go through the channel. So the more current we could be drawing, or the higher, relative to the voltage we'll drop across the channel. So right now we're driving with 12 volts. As we increase voltage, this spike gets worse or bigger, and that can be bad. And I swear I had a second point and now I forgot what it was. What's a factor of 100 among friends? Yeah. Okay, so this is actually pretty cool because this means our MOSFET turns on relatively quick. And on the next setup, I'm going to do a math function where we see how much power the MOSFET dissipates, but it gets really confusing. Instead, I want to show you my magic probe number 4. So I'm going to turn on channel 4, and I'm going to set it to a 50 ohm input and limit it to 20 megahertz because the probe is only good to about 30 or so. And then, the probe that I have. And then we're going to crank it, so I'm changing the volts per division to, let's say, 10 millivolts. And now I'm going to turn this knob up here and put it down to about here. So let me switch to this real quick. What I've got going on is this probe, and I'm going to take and I'm going to place it right here next to the MOSFET. And we'll, okay, so it was just a little bit more. There we go. And this is what I want you to notice. So all I've got, so this is called a near field probe. It's basically like a coil. And the idea is if there's an electromagnetic field, it actually induces a current on the probe, which then creates a voltage, which we measure with the scope. So just by placing it right next to the MOSFET, that's all I've done. It's not making real physical contact. It's a contactless measurement. Now, when we go and look at this, I'll leave it over here just so it's clear what we're doing. Oh, I'm zoomed in all the way. Notice now this purple signal. When the MOSFET turns on, it is creating a huge EM field that we're picking up with the probe. And so just by switching this on so fast, the probe is kicking out a huge inductive spike. I'm sorry, a huge electromagnetic spike. And so when you hear about things being EMI sensitive or having to go through EMI compliance or EMI testing, this is an example of where a MOSFET that is switching creates that EMI that we have to and want to avoid. You know, what's surprising to me is I'm not physically touching. I'm probably on the order of half an inch to maybe a quarter of an inch away, which would be, I don't know, let's call it 10 millimeters. Or is that 10 centimeters? I always forget. So really close, but this purple waveform is bad. That's something that we want to avoid. So the spike, isn't it due to the parasitic inductive components? There's not really anything in the circuit that's highly inductive. There is an inductive spike from the inductive elements of the MOSFET, but I'm sure that plays into this, but it sort of doesn't matter. It's the total MOSFET itself. Because of the rate of how fast it's turning on, we get this spike. Okay, so let's do this. Let's I'm gonna save this point. Let me hit the screenshot button in case we need to come back to it, but I've got other screenshots that look a lot like this. So what I'm gonna do now is I'm going to switch to our 3K resistor board. So let's go to overhead, and we'll leave that on. Why not? We'll bring this up. So what I'm going to do is disconnect our Arduino, turn off the power supply just in case. Wow, that was some noise. Remove this probe and this probe, and then we will now remove our load resistor, which is 100 ohms. Which, by the way, it's only rated for a 1/4 watt, but we're putting 1 watt through it. And so that's why I have the Arduino turning on and off, so that we can kind of get reduced current or reduced power dissipation on it. But it was the only 100 ohm that I had, and I didn't want to go much smaller than that, because then we just get into all kinds of other effects. I'm still kind of bummed that my electronic load just does not respond well enough. That was an unfortunate discovery. Let's get this guy in here. That must not be. Put this one in here. All right, so that's connected, that's good. We put this probe. So current probe stays the way it is, it's clamped on, which I actually have an upcoming Element 14 video on how to measure current, so that probes like that will be coming back. All right, ready to turn this on. And we should see the gate switch, we do. Then we can turn this on. Okay. Uh-oh. What is going on? That is ground. This is pin 3. Why isn't the Arduino doing anything? Did I skip something? Oh. I forgot to hook the source back up. The source pin, I mean. There we go. Okay. Move this over so we can see more what's going on. Super clean circuit setup here. Okay. There we go. Okay. What load do you have? Right now we just have a 100, the electronic load I have is a BK Precision 8540. It's really meant for production. It's not really meant for lab usage. And so it works well enough most of the time, but in this case, it just didn't turn on fast enough. So that's why I'm using the 100 ohm resistor. So okay. Now, what do we notice the first thing? What is the first thing we should notice? So the gate turns on, and like I said before, it's relatively straight up. But notice this time that our voltage and our current seem to be not doing anything. And that's because it's taking much longer for the transistor to turn on. So I'm going to zoom out. And it turns out we have to go quite a ways in order to finally see any activity. And that's not a surprise because we're using a 3K resistor in this circuit. And so remember I said there's a capacitor on the gate and then there's a capacitor between the gate and the drain. And so that 3K resistor is going to significantly limit how fast those two charge, which is exactly what we see going on here, is that we don't get the same characteristic Miller plateau because the gate charges up to 5, and then it just takes a really long time before the drain can start to turn on. And by that point, the gate capacitor is already charged up. We were actually just taking that long to charge the drain capacitor, which is when it finally starts to turn on. And so what we'll notice is there's no inductive spike when the gate turns on. And the other thing, like I said, is it just takes a really long time to turn this on. I'm also going to take my near field probe and put it right next to the transistor, and notice how this time we do see a little bit of noise. This is the same scale we had before, but it is nowhere near as bad as it was. And so just by slowing down how fast the transistor can turn on, we eliminated the EMI that we were creating from this transistor. The reason we use gate resistors, well, one of the reasons we use a gate resistor on the transistor is to fundamentally slow its switching down so that we don't get effects like EMI. Another reason might be is because we want to do a soft start, and so we don't want to have shoot through happen, or we need to actually delay the time between different stages. So there's other reasons, but to me, this is the easiest one to demonstrate, is we get much quieter performance. It does come with a trade-off though. And so what I want to talk about now is what we call switching losses. So if I move my cursors over, we can see now that the time it takes for the transistor to turn on is on the order of 7 microseconds. And so it is really, it is taking really long compared to no resistor, right? With no resistor, it turned on in 100 nanoseconds, and now it's an order of magnitude longer, which is actually 7 microseconds. And so to me, this is a challenge because, why is this? So why is this a challenge? Or why is this not, I mean, one bad thing about this is it just takes a long time to turn on. But the other thing is, let's think about what's going on. As the voltage drops, the current is going up. And what is power dissipation? Power dissipation is voltage times current. So what I'm going to do now is turn on a math function. I'm actually going to stop the scope just so, I don't know, you guys probably can't hear it, but when the power supply turns on, the transformer makes a terrible buzzing noise and it's driving me crazy. So, okay, so I'm going to turn on a math function, and the math function that we have is channel 1 multiplied by channel 2. I said that backwards. Channel 1 multiplied by channel 2. So this will effectively show us the power dissipated by the MOSFET. And this is why the oscope wizard was giving me a hard time earlier, because if there's skew in our measurement between the current and the voltage, then this measurement doesn't work. But like I said, I more or less took care of that. So let's make this a little bit bigger, just so we can see what's going on. And this is, we would have seen this same kind of shape if we looked at this with a 0 ohm, but it's just so small, the time is so small, that I thought it was more interesting to look at it here. Now what I'm going to do is move my cursors to the math waveform, which is, I called it power. And then that way, what we can look at is I want to move it over to this peak. And so right here, oh, I need to change the type. Cursor, let's go to V marker, back. And so what we can see is at the peak, this transistor is dissipating 50 wrong one. It is dissipating 368, let's call it 370 milliwatts. And so just by turning on, the transistor is heating up, which is terrible because if we look at the other cursor and move it over in time, when the transistor is finally turned on, it only dissipates about 50 milliwatts. And I would actually say it's less than 50 milliwatts because we're probably not getting a good current measurement. I didn't go through a lot of effort to get a solid current measurement. There's some noise and stuff like that. But I think the comparison between the switching time, it's dissipating a couple hundred milliwatts, and then when it's on, it only dissipates like 50 milliwatts. And so what we call switching losses are basically this bump in the curve right here. This is power that just gets wasted. Now, if you're on AC mains, the wasted power isn't usually necessarily the bad thing. But what does power generate? What happens when you have more power dissipation? Yeah, the switching losses can be the biggest losses in motor control. Actually, yeah, motor control, even power supply designs, so really high current, high power designs, they have, one of the reasons that designers don't like to use P-channel MOSFETs is because their on resistance is a little bit higher, so their overall switching losses are higher. But this is the challenge we have. We want to switch as fast as possible to limit the switching loss, which is what we're seeing here. On the other hand, we don't want to switch any faster than we need to because we don't want to create inductive or EMI effects from that fast switching. And so you generally want to kind of find a happy medium between the two. So as a cliffhanger, the next measurement I'm going to end up making is change the resistor to something more reasonable, because here we've compared 0 ohms to this is currently 3K, which is way too much. It just happened to be what I had when I soldered the circuit board. But the next step would be is to put a 10 ohm resistor in here and see what that looks like, because now we're starting to get into more of a realm of what is an appropriate value. Now, you might be saying, well, how do I know what value to pick? Okay, so then now you're going to get into having to calculate gate charges and such. So if you're designing, I would say, a product you intend to sell where things like cost and safety and EMI are an issue, then there's a whole bunch of math that I'm just not going to get into what you do. But for a one-off project, what I would say at a minimum is put some test points so that you can do things like measure what does this gate signal look like. Because if you can see the nice Miller plateau and you can see any kind of ringing effects that it has, then you know whether or not you need more or less resistance. I also get lost in motor control after designing circuits for a long time. Good one. Oh yeah, and then matching infets is a real pain. Yeah, that's a whole nother issue. In fact, let me go back to this screenshot. One of the things, like if you think about like a motor controller where you have multiple FETs connected together, One thing you might want to do is like the adjacent FETs for forward and backwards. You want those, well, that's for a H-bridge, but even in a brushless controller, you want this plateau time to be about the same. And unfortunately, every manufactured MOSFET is going to be different. If you look at the datasheet, just like the VGS threshold, there's a range in which the MOSFET turns on. Until you measure an individual MOSFET, you don't know what it's going to be. Which is another reason why you would want to have like a series resistor that would allow you in manufacturing the potential to do some kind of adjustment. And then if you're doing a power supply with what we call a high side and low side, where you're actually basically what you're doing, or I say power supply, but it's I'm thinking of an inverter where you're actually generating like an AC waveform from DC. You do that with a transistor. You turn it on to a high voltage and then you turn it on to ground, and it causes the waveform to kind of do up and down, up and down. In that case, you have to be very careful about your timing because you can't have the MOSFETs turn on at the same time. And so you have to figure out how long does it take for them to turn on so that you can adjust that in your controller. So this leads to lots of other things, as you can see. Ultimately, what I'm headed towards is a video and write-up that talks about, yeah, for most circuits, the VGS threshold voltage is enough to get a circuit designed in. But if you start getting beyond, I'm just using the MOSFET to turn on something at a relatively slow rate, we really have to start looking at some other characteristics of it. And that's where that's where I wanted to go. What I really like about this is, and these two sets of measurements were not what I originally intended to build this board to do, but I'm glad it worked out because I really like that with a 0 ohm resistor, we can see the Miller effect, and with a ridiculous gate value resistor, we can see the slow switching effect. Now, I would argue if we're in a situation where the MOSFET is only turning on once per second, then something like this 3K resistor is probably fine because you're only going to have this switching loss occur every so often. It will depend on how much voltage you're applying to the drain and how much current you ultimately want to drive through the MOSFET. But I mean, generally this is only a few microseconds. And so once it's turned on, it should start to cool down a little bit. So, yeah. So Peter, I don't know how to say your username. Is it Eston? Because I realized I've only ever heard you say your first name. I never heard your last name. Anyway, but yeah, so I'll just say Eston. Eston? It has to be Eston. Okay. He's talking about, I mean, a really super common place where you run into what I'll call legit MOSFET design is when you're looking at a brushless motor controller, because that's where all of the real MOSFET effects come out. When you're just turning on, like we're just turning on a single load relatively slow with an Arduino, I think we're in a situation where could you get away with no gate resistor? Probably. Should you? I still think you're going to want to have something on the order of 10 to 100 ohms. And that's why I say that's going to be a cliffhanger, because that's the next step I want to do is make those measurements, since that's a more realistic resistance value. You really wouldn't put 3K ohm on a resistor, on a gate. That's just too many ohms. And I know I like to say you should add ohms. Sometimes you should only add as many ohms as you need. Okay. Will this stream be saved? Yeah, so the stream, I actually save all the YouTube streams. I don't publish them. What I would actually recommend is you go to twitch.tv/baldengineer, because I save all of the streams there. I do a highlight of the stream so that it doesn't get deleted. And then at some point I'll go back through and actually clip out pieces from this explanation so that you could jump around to specific pieces. But I think the best thing to do is go over to twitch.tv/baldengineer, because that's where I'll catalog it. Twitch's tools for handling stuff like taking clips out of a longer stream are just significantly better than YouTube, and I can't stand using the YouTube interface. So, okay. Yeah, I think this is what cracks me up about this is I still haven't made the measurement that I designed the board to do. And so, but I think this really helps to illustrate the, what illustrated for me is when I was in school, I remember learning about this stuff. And in my professional career, I've talked to power supply designers who have brought these issues up, but this was the first time I could actually see it and then manipulate it. So I think that's pretty fun. Yeah, actually, I think not in the next couple of months, but on my list of the things that I want to design, I do want to design my own brushless motor controller just for the sake of learning how to do it. Just like I want to do my own inverter design and things like that. I have absolutely zero intention of making a high efficiency or even well designed, but just like this board, I like to design up these circuits and then just see how they work, because that's how I learn. That's how I get the things that I heard once 2 decades ago reinforced. Okay, what else should we do? I want to make, so I showed you the power dissipation. We see the gate, the power turn on, the amount of time. I think I showed you all the measurements I had wanted to show. The only other thing I was going to say, the only other one I had meant to talk about was how long it took my load to turn on, and that was how frustrating that was. Let me just see real quick if I have a screenshot. Nope, that's not it. Yeah, okay. So here's let me just talk about this. So this was what I was originally measuring, and this really threw me for a loop. So this was with my electronic load. And if you remember, it's a programmable resistance. What it really is internally is it's a P MOSFET, P-channel MOSFET that is microcontroller controlled. And in this case, I had it set to a constant resistance of 100 ohms. And so what was going on is I saw the gate turn on, and I saw the drain turn on, but I would see the current like shoot up and then come back to zero. And I was like, what in the world is going on? Because that doesn't make sense, right? Everything we saw is the current should turn on and then stay on. And so I disconnected everything. Oh, why'd you do that? Why did that happen? Hey, thanks for the follows. I couldn't catch the names, but I do appreciate you following. Yeah, so I was like, what is going on? And the first thought I had was, well, maybe my current probe is just out of, is not de-skewed. And so then I disconnected everything, and then I hooked up just the current probe and the power supply, and I noticed that the load would turn on nice, slow, and then do this. And so this curve looked right, this one looked wrong, and I couldn't figure out what was going on. And so eventually what I figured out is this screenshot. So this is when the transistor turns on, and you can't see it because the cursor's in the way, but there was a little glitch happening. And so when the transistor would first turn on, the load would be super high impedance, super low impedance. It would actually show like a current of like 10 amps for a couple of nanoseconds. And then 250 milliseconds later, it would turn on correctly. And so this delay was driving me insane because I couldn't figure out what was happening, which is why I switched to a traditional resistor, because it was completely screwing with what I thought was happening. So fun times. So Vince, like I said, the best place to see the repeat of this is going to be on twitch.tv/baldengineer. Although I might repost this one. I might go ahead and let this one get published to YouTube, just because we got through everything without a ton of problems. So, okay. The only other thing I have to talk about then is our op-amp circuit, but I sort of don't want to get into that because I've got to break everything down and reset up a bunch of stuff. And so I think we're going to save that for Sunday. Friday, let's go ahead and do this because that's what I was trying to get to. So Friday, I think we're going to do a LCD replacement either in an Atari Lynx or a Game Gear. Actually, it's probably going to be the Game Gear because I think the Lynx doesn't turn on and I don't have the MOSFET that we need to fix that. So I think that's what we're going to be doing. Yeah, it's almost like I planned it that way so that our stream days don't overlap. That actually reminds me, I did want to start, I want to add a list of other streams below mine in the description area because I think there's a lot of really cool electronics people starting to do stuff on Twitch, and so I want to make sure we share with each other. And so anyway, so that's what I'm thinking is, so Sunday we're going to go back to the op-amp circuit, and then on Friday I'm going to try to stick to Fridays being something video game related. And so I've got a replacement LCD for a Game Gear that if I've got all the pieces, we'll do that. And if not, then I've got a couple of solder type projects we can do instead. But I think it'll be just kind of fun to do something kind of, I mean, this MOSFET stuff is, to me, really fun and exciting, but it takes a lot of brain to figure out what's going on and then explain it. And so I'd rather so on Fridays, I like to do something that's a little bit easier. Okay, Moldavia, I have a game for you 2 ways. I'm not sure what you mean by that. Okay, Def Bomb, yeah, I do Sunday morning California time, and we're -7 hours GMT. Okay, game to stream. I thought you were gonna give me a drinking game. Yeah, no, that's fine. We can do that. Yeah. So, yeah, I don't want to get this. I really want to do this tonight, but I feel like this is. I want to keep on topic. So, okay, I'm gonna wrap up. Let me do my usual ads. First, thanks to everybody in the chat for participating, asking questions, helping out. Always appreciate that. I actually really like it when I see somebody ask a question that's a little bit unrelated to what I'm doing, and then other people can chime in and help. I think that makes it a fun and interesting community. If you want to keep the conversation going, we do have a Discord. The easiest way to get there is to go to AddOhms, AddOhms.com/Discord. So basically AddOhms.com/Discord. It'll redirect you back to the Discord server. And that way we can keep in touch. Just like this MOSFET thing. So after Sunday's stream, as I was figuring things out with what was going on, I was posting in there, keeping people up to date, as well as getting some feedback so that I could understand where the explanation was at. The game Rogue Bit. Interesting. I don't know that one. Bit 101. It's based on you. I'm curious what that means now. Okay. So yeah, so the Discord. Okay. Let's do that. I want to thank everybody for coming. We'll be streaming again on Friday evening Pacific time. I'm going to start a couple of hours later than I did today. So in fact, we'll actually be starting right about this time on Friday. And then there will be one Sunday morning. And I think we know what the topics are going to be on both of those. For the moment, I want to thank everybody for joining. I also want to give a shout out to Patreons. I do appreciate people who are supporting me on Patreon. It does actually help pay for stuff like the PCB and the components. Anything that I do as AddOhms or the Bald Engineer comes out of my pocket, and so I have to buy things like this stuff. So I appreciate that support because it helps to offset some of those costs. With that, I want to thank everybody, and I will, you know what? I know what I was going to do. I was going to start saying, okay, if your circuit isn't working, remember, just add ohms. However, unless it's a MOSFET gate driver, in which case you don't want to add too many ohms, but you do need to have a couple of ohms. All right, guys, thanks a lot. If you find these videos helpful, please consider supporting AddOhms and the Bald Engineer on Patreon.